Hello, my name is Mr. Asprey, and I've got 3 questions today to do in the A-Level Tricky series, and these were sent by a student, and they're all on parametric equations, and I thought they all looked interesting, all look difficult for different reasons, so let's just give them a go and see how we get on. So the first one, we're asked to find a Cartesian equation. Now, if you've not done parametric equations before, parametrics are a set of equations which model a curve in this instance, and they are given by a third parameter, in this case t. So in order to find a Cartesian equation which relates x and y, we need to eliminate t. Now this looks quite tricky because we've got t occurring twice in both the x and the y, and it's not quite so obvious as to how you're going to cancel out the t's. But what I'm going to do is I'm going to write it out like this. So x is equal to t minus, and that is t to the minus 1. And then I'm going to divide both sides by 2 for this equation, so that I just get t plus t to the minus 1, like so. Now if I were to maybe subtract these equations, the t's would cancel out nicely, but the t's to the minus 1s wouldn't. Or if I were to add them again, the t to the minus 1s would cancel, but the t's wouldn't. So the trick here is to square the equations. So I'm going to write x squared, and I'm going to square that side. And here I'm going to square here, and I'm going to square there. Now what's that going to give us? Well, over here we're going to do t minus t to the minus 1 times by itself. And that will give me t squared. T times minus t to the minus 1 will be minus t to the 0, which is just minus 1. And then here we're going to also get minus 1, so that makes minus 2 in total. And then this last term will be positive because the 2 minuses, and that will be t to the minus 2 because we add the powers when we times t's. Okay, great. Now let's do the same for this one down here. So we'll be multiplying it by itself because we're squaring, and that's going to give me t squared. It will give me plus 2 this time because there's no minuses there, and it will give me plus t to the minus 2 as well. Perfect. So now what we can do is we can subtract one equation from the other, and that is going to cancel out the t squareds. When we subtract, those will cancel, and it will also cancel out the t to the minus 2s as well. And that's exactly what we want to do because we want Cartesian, which means no t's, just x's and y's. Okay, so the left-hand side of the equation, when I subtract, I'll get x squared minus y squared over 4, which is this y over 2 all squared. And then when I subtract these ones on the right-hand side of the equation, the blue t squareds will cancel, the yellow t to the minus 2s will cancel, so we're just left with minus 2, take away 2, which is minus 4. And bosh, there it is. That is Cartesian because it is x and y's, no t's, no third parameter. We are good to go. On to the next one. Okay, next question. We've got some trig involved. We've got x is equal to tan squared t, y is equal to sine t, and it's asking us to find dy by dx. Now, parametric differentiation. If I'm trying to find dy by dx, what I need to do is I need to work out dy by dt, and then divide it by dx by dt. And you can see why this works because the dt's on the bottom could cancel out, and we get dy by dx on both sides. So that is legit. That works because of the chain rule. How lovely. Okay, just trying to get rid of these lines. Perfect. Okay, so that means I need to first off differentiate this with respect to t. That's going to go on the top of my fraction. Well, sine to cos, sine differentiates to cos. So yeah, we just get cos t on the top. And you can also remember that cos to sine, you change the sign, but sine to cos you don't. So there you go, still positive. Now I've got to differentiate this. Now that's a bit trickier because we're going to need to use the chain rule for that. So I'm just going to go over here and I'm going to write that x is equal to tan squared t. So we could say that x is equal to u squared, where u is equal to tan t. That works, yep. And then we can do dx by du is equal to 2u, just differentiating with respect to u. And then we could do du by dx, du by dt is the derivative of tan, which is in your formula book. If you don't know, you can look it up. It is sec squared t. Okay, perfect. So how do I then find dx by dt using the chain rule? Well, dx by dt is equal to dx by du multiplied by du by dt. So we have 2u multiplied by sec squared t, which is the same as 2 times by u, which we know is tan t. That was the substitution we did, times by sec squared t. Beautiful. So that goes on the bottom of our dy by dx here. So that gives me 2 tan t sec squared t. And it says you do not need to simplify your answer. Perfect. Get rid of that working, and we will move on to part B, where it's asking us to find the tangent to the curve at the point where t is equal to pi over 4. Fine. So to find the tangent, I'm going to need to know the gradient when t is equal to pi over 4. But first, what I think I'll do is I will actually simplify this guy over here to make it easier for me to substitute in, because I don't want to use a calculator. So what have we got here? Aha, I know what we've got. We've got cos t, and we are dividing by 2 tan, which is sine t over cos t, multiplied by sec is 1 over cos, so sec squared is 1 over cos squared. Okay, so this gives me cos t, and we are dividing by 2 sine t over cos cube t. Now when we get this situation where we're dividing by a fraction, what we could do is we could flip that fraction over and multiply. So we're actually going to multiply cos t on top by the reciprocal of 2 sine t over cos cube t. So this is going to give me, basically that cos cube is going to flip to the top. So it's going to become a cos to the 4t over 2 sine t. Now that's really helpful, because we know from our exact values of trig that cos of pi over 4 is the same as sine of pi over 4, which is equal to 1 over root 2. In fact, 1 over root 2 is also the same as root 2 over 2 when we rationalise. So maybe it's easier to substitute that in. So we are going to sub into the gradient function. So we have root 2 over 2 for cos t, which we need to raise to the power 4, over root 2 over 2 times by 2 on the bottom. Okay. I know people might be shouting at me, just use the calculator. Yes, perhaps, but this is more fun, so no. So a root 2 over 2 can cancel, because we've got 4 on top and only 1 on the bottom, so they cancel away. And then when I cube this, when I cube root 2, I get 2 root 2. When I cube 2, I get 8, and that's all over 2. That cancels with that, so I get a gradient of root 2 over 8. Okay, in order to find the tangent, I also need an xy coordinate. So I need to sub into the x function a value of t at the particular point where we're trying to find the tangent. So this is going to be tan squared of pi over 4. Tan of pi over 4 is 1, so square it, still gets 1. And then when we do y, it's of sine pi over 4, which is root 2 over 2, as previously stated. Fantastic. So we've got all the ingredients now to find the tangent. We've got the gradient at the point, and we have the point itself. So we should be good. My favourite formula for a straight line is y minus y1 equals mx minus x1. So we say y minus the y coordinate at the point, which is root 2 over 2, is equal to the gradient multiplied by x minus the x coordinate. And in fact, let's just write this out now in a more usual form. So we have minus root 2 over 8, and we add on the other root 2 over there, root 2 over 2. So we get y is equal to root 2 over 8x, and that is going to be plus 3 root 2 over 8. Right, brilliant. This is screaming out for trig identities. So I'm going to start with the x is equal to tan squared t, which is of course sine squared t over cos squared t. I can see that they're asking it in the form y squared, so it would be a good idea to square y, which will give me sine squared t. Okay, so the idea is to eliminate the t's. So what I'm going to want to do is substitute one equation into the other. Now, I've got an expression for sine squared. Ideally, I'd also want an expression for cos squared. And we know that sine squared is 1 minus cos squared, because of course sine squared t plus cos squared t is equivalent to 1. Okay, so now I can rearrange to make cos squared the subject of this, and this gives me 1 minus y squared. And then we've now got an expression for cos squared, an expression for sine squared, and we've got an expression for x in terms of sine squared and cos squared. So let's substitute into this expression over here and say that x is now equal to sine squared, which we've said is y squared, over cos squared, which is 1 minus y squared. We need y squared to be the subject, so we're going to have to do a bit of GCSE maths here and just rearrange for y squared. So I'm going to multiply up by that denominator, like so. I'm going to move all the y squareds over to one side. I'm then going to factorize out the y squared to get x plus 1. And then finally I'm going to divide through by that factor of x plus 1. And we are good to go. Bosh. Okay, lovely. Question 2 done. On to question 3. Okay, we got a fish. We got a fish. Beautiful. Look at this. This is a parametric equation, and you've got the x and you've got the y, and it says that the curve C cuts the x-axis at A and B. Find the coordinates of A and B. Well, if it cuts the x-axis, then we know that along that line y equals 0. So we're going to set the y equation, which is this one, equal to 0. So 0 is equal to t 9 minus t squared, which is perfect. It's factorized already, so we can just pull out the solution. So t equals 0 from that one, and from this one 9 minus t squared equals 0, which means t squared equals 9, which means t equals plus or minus 3. Okay, now let's then sub into the x to find the corresponding x values at those particular points. Now my guess is that this point B is going to be the t equals plus minus 3, because the curve comes in and it hits B twice. It goes in once and then it comes in a second time, so it will make sense that it has two t values, which means that this one I suspect will be t equals 0. Let's confirm that suspicion by saying that x is equal to, or let's start, so t equals 0 implies that x equals, what's the x equation? We're going to take the t and square it, and then minus 4. So we're going to get minus 4. So that gives me that must be a, because it's negative as well. So it's minus 4, 0 for a. Okay, lovely. And now we'll do the positive t is equal to 3. In fact, it doesn't matter, does it? Because you're squaring it. It's the t squared which is going to be used here. Sorry. So the x coordinate is 5 multiplied by t squared. T squared we said was 9 minus 4. So that's 45 minus 4, which is 41. So the b coordinate is 41, 0. Okay, great. And now it says that we're going to use algebraic integration to find the area enclosed by the loop of the curve. Okay, great. So what's going to happen is, let me just check. When t equals 1, the x coordinate is equal to 5 minus 4, which is 1. Okay, and the y coordinate, that wasn't helpful at all actually, is equal to 1, 9 minus 1, so that makes 8. Perfect. Okay. So t being minus 3 is here. And then it goes along here to get here where t equals 0. And then it comes along, so I say t is equal to minus 3 is here. And then it's t equals 0 gets to there. And then it comes up here and we get t equals 1 where the y coordinate is positive, so that I know it's that side. And then it's going to come back here where t equals 3. So the reason why I checked that is because that tells me that this curve, which is the one I want to integrate, is from t is equal to 0 to t is equal to 3. And I'm going to integrate that, and when I do integrate it, it's going to give me the area between the curve and the x-axis. So it'll give me that area, and then I will double it to get the overall area. Okay. So the formula for parametric integration is y multiplied by dx by dt dt. And that's going to give me half of my region. So let's say that the region is equal to 2 lots of that. Okay, so r is equal to 2 lots of the integral of y, which is t 9 minus t squared, multiplied by dx by dt, and the derivative of the x function is 10t, because the 2 comes down, times by the 5 to make 10, drop the power down by 1, and the minus 4 is a constant, differentiates to 0. Bosh. So 10t. And that is with respect to t. And we need our t values, which we've shown from this diagram, are t equals 3 and t equals 0. We're integrating between those two t values. Brilliant. Okay, so let's now integrate this function. First, in fact, let me expand out. So I get t times 9 times 10t is 90 t squared. T times minus t squared times 10t is minus 10t to the power of 4. Let's put that in brackets and then apply the dt. And now let's integrate. So we up the power, then divide by the new power. So up the power to 3, divide by 3 gives me 30. Up the power to 5, divide by 5 gives me 2. And that's between 3 and 0. Okay, so now we can just sub in 3. And that's 27 times 3 is 81 times 10, so that's 810. And that is 243 doubled is 486. Why can't I just use a calculator? And that is 324. So that gives me a total of 648, and there's no units, so I could just leave it like that. Right, I really hope you enjoyed that, and stay tuned, stay subscribed, because throughout the year, and particularly around exam seasons, I'm going to be doing loads of tricky questions to get you prepared for your exams. Bye for now.